Now, so far, we have done principal component analysis using the covariance matrix, so using the empirical data. So we've taken the covariance matrix, the empirical covariance matrix, S, which is X transposed HX. Now, sometimes we're told the distribution of the data. So there's some cases where we're told that vector X is a random variable and that it has mean equal to mu and that the variance of X equals to sigma. So later on in a later chapter we will see multivariate Gaussian distributions, for example. Okay, but just for a moment, just suppose X is a random variable and it has some mean vector mu and some covariance matrix sigma. So there's nothing estimated here. This is the mean of the population and the covariance of the population. Now there's a version of PCA that instead operates on this covariance matrix. So if we write down the spectral decomposition of the covariance matrix sigma, this is going to be the sum. Apologies for the two sigmas here, but this one's a sum. The sum from J equals 1 to P of lambda J V J V J transposed, or in the notation we had before, V gamma V transposed. Okay, and to distinguish these quantities from the population quantities we had before, I'm going to put a check mark above them all. Okay, so it matches what's in the notes. So these are the eigenvectors Vj of the true covariance matrix sigma. Then we can still do a PCA-like transformation of the data. So we can define random variables. Let's define y1 to be v1, that's a check version of v1 transposed x minus mu. Okay, and similarly we can define yp to be vp transposed x minus mu. So these are random variables now, because x is a random variable. And essentially what we're doing here is subtracting the mean from the random variable. So these are going to be mean 0. So the expected value of yi will be 0. And then we're decorrelating them. So just as we did previously, and we're not going to bother proving it now, okay, but just as we did previously, what we're going to find is that these principal component scores, so these are our scores or transformed variables, so they're going to be mean 0. They're also going to have variance given by the eigenvalues, check, okay, and the correlation between yi and yj is going to be 0. So we're not in this situation very often where we actually know the true underlying population variance, but if we are, we can transform the variables in this way. But the useful way of thinking about this is this gives us an idea, statistically, of what the principal component analysis is doing. So we know that if we have data x1, xn sampled from this distribution, then the empirical covariance matrix, I'm going to put an n on it here just to indicate that it's based on n data points, x transpose x, okay, or hx, say, if we center it. Well, then we know that Sn is going to converge to sigma as n tends to infinity. And consequently, we're going to find that the estimated principal components, the I, are going to converge to the eigenvectors or the principal components of sigma. Okay, sigma and lambda j is going to converge to lambda I hat, okay, all as n goes to infinity. So we're not going to get into the details of this, but this is how we justify doing PCA, justify and give meaning to the quantities we estimate from PCA. In the theoretical limit, as we collect more and more data, the principal components, the eigenvalues and eigenvectors, will tend towards the eigenvalues and eigenvectors of the true underlying covariance matrix. But as I say, we're not going to get into the details, and it's beyond the scope of this module to give a proper analysis of this. So let's now think about what happens to PCA when we transform the data in different ways. So first of all, let's just consider transforming the data by addition. Let's suppose instead of doing PCA on the x's, we instead do PCA on z's, which are the x's plus some constant. So the first question to ask is, does this change the analysis in any way? Okay. Well, first of all, it should be obvious. If not, you can check it, that z bar is going to be x bar plus c. And so when we work out the covariance matrix of z, that is just going to be the sum of zi minus z bar, zi minus z bar transposed times 1 over n. And you're going to see quite quickly, if you think about it, that this is just the same as the covariance matrix of x. Okay. So, in other words, adding a constant here is not going to make any difference at all to the principal components analysis. So, PCA is invariant under addition. So the next kind of transformation we're going to consider then is scaling each variable. So let's suppose some component of x is a distance. Now we could measure the distance in meters, or in feet, or yards, or miles, or kilometers. Okay. And the question is, does that change the principal component analysis at all? Okay. So if instead of analysing the x's, we instead analyse zi, which is d times xi, where d is a diagonal matrix. So this is multiplying each variable by some constant. Does that change anything? Well, yes, it's going to. If you think about the variance matrix, the empirical variance matrix, the empirical covariance matrix of z is going to be 1 over n sum of dxi minus dx bar, because the transformation is going to change the sample mean by d as well, times dxi minus dx bar transposed. So you're going to see that this is d s of x. Okay, so the sample covariance matrix for x, d transposed. D transposed is d. Okay. So the eigenvectors of the covariance matrix for z might be different. They will be different to the eigenvectors of the covariance matrix for x. Okay. So scaling will change the principal components. Okay. So for example, changing units of measurement, right, miles to kilometers, for example, will change the answer you get in your analysis. And that's often undesirable. Right? That's not something we should be too comfortable with. So one thing we often do is first to scale all the variables each time, to put them on a common scale. If we let D be the diagonal matrix that is 1 over square root of S11 down to 1 over the square root of SPP. Okay. So where SII is the ith element of the covariance matrix of X, then what we're doing, we're standardizing all the variables. We're going to find that the sample variance of Z, which is D SX D, is now going to be R, the correlation matrix. So we can instead then, we can do PCA on the correlation matrix R instead of S. And so we saw that in the previous section. Okay? And that's often a desirable thing to do. So we talked about how we can do this in R with the prcomp command. You have to set scale equal to true when you run this, okay? And that will do principal component analysis on the correlation matrix rather than the covariance matrix. And the nice thing of doing that is then that PCA on the correlation matrix is scale invariant because it scales all the variables for you. Okay? So it doesn't matter if you scale each variable. Working with the correlation, it essentially unscales them back to all having variant 1. And then just finally, we're going to consider the case of orthogonal transformations. So let's consider A, which is a P by P matrix that's orthogonal. So let's say A transposed A is the identity matrix. And let's let our transformed variable Zi be A times Xi. And what happens to PCA in this case? Well, first of all, note that the covariance matrix of Z is going to be A, S, A transposed. And if we substitute in the spectral decomposition for S, so if that was V lambda V transposed A transposed, then we can see that we could write this as AV times lambda times AV transpose. Now, if we let B be AV, then B is an orthogonal matrix, so B transpose B is easy to check equals to identity. So this, the spectral decomposition of SZ becomes B lambda B transposed. So essentially what happens when we multiply the data by an orthogonal matrix A is we multiply the principal components, the loading vectors, the eigenvectors, by A as well. So that eigenvectors BI are A times VI. Now the transformed variables, our principal component scores, well, they are going to be B transposed ZI minus Z bar. Well, let's see what that works out as. Well, B was AV, so this is V transposed A transposed. ZI was A XI, and z bar will be a x bar. So let's multiply through by A transposed. We know A transposed A is the identity, so this just works out to be V transposed xi minus x bar. So transformation hasn't changed the principal component scores at all. The transformation by orthogonal rotation does not change the eigenvalues or principal component scores. It does change the principal component loadings, or the eigenvectors, as they're often called.